How's it going? All right, round two. Here's kind of my setup. Nothing too crazy around me. It's me and this sheet of paper. Using this little rotisserie. I'll kind of reference it back and forth like I did last time. So this is a lot like the last one that I did, but we're doing a uniformly charged disc. And so just like last time, we'll start off, I'll draw just a very poor diagram of kind of what we're trying to do here. But we have a point P observing above this disk at distance Z. This disk will also have a radius R. And then one thing that we'll be utilizing for this problem is the idea of rings. And the rings, when we use these rings, it allows us to break the disk up into smaller pieces so that we can work with it better. So for the radius of those, and we can get into it a little bit more later, we'll use like a radius S. Okay, that's kind of what we're working with so far. Nothing too crazy. And we can just start off, we know that we're going to be using Coulomb's law here. And then we also, just like the last problem, is set up in a way that I can get into a little bit later. But so we have dE equals K dQ over R squared, right? And then, I need, oh, sorry, on the diagram I need to put, we also have dQ, which is a point charge on the disk itself. Basically what we're trying to do is add all these up to determine our electric field. So that's what we're trying to integrate at the end. So we're trying to solve for that. So let's do what we can geometrically to solve what we can. So one thing that's very important is that the X and Y components of these cancel out because they are symmetrical, right? And that's the only way that we're able to solve a problem like this, because it leaves just the Z component, at least in what we're doing here. So we'll rewrite this as dEz equals dE cosine theta, right? And then we can just start solving for like what we do know. So, and we are going to be using the ring. So we know that R geometrically will equal the square root of Z squared plus S squared, right? And then we also know that cosine theta, excuse me, I wrote that wrong, cosine theta is equal to Z over R. So I'll update, nothing too crazy. And then we can just plug that back into our formula that we just wrote for dEz. So we have dEz equals to, and then plug in what we had earlier, K dQ over, and then we'll plug in our new R. So we have square root of Z squared plus S squared times Z over the same thing, plug in again, Z squared plus S squared. Simplify that, we'll have K dQz over, and then we could simplify this and we'll say this is Z squared plus S squared to the 3 halves, right? Okay, so now, and like I said, our objective is to integrate dQ, right? And one way we can do that, we know that the area of these rings is, well, we know that dQ is equal to omega dA, right? And And then we know that dA is equal to 2 pi SDS, right? So 2 pi SDS. And then we can combine that all together. And so we know that, yeah, dq equals omega 2 pi SDS. Yeah. And then we can plug that back into our formula and integrate for dq. So just big picture, we have E equals K times omega 2 pi SDS. Oh, and then we also have Z all over. Oh, I also forgot the integration. And we know that the integration's bounds are from 0 to R. And then that's all over the Z squared plus S squared to the 3/2. And as you can tell, a lot of these are actually constants, so we can pull those in front of the integral. And let me just do that now. So we'll have Z K omega 2 pi. The S will stay in the numerator. And then so we'll say integral 0 to R of 0 to R, and then of S over Z squared plus S squared to 3/2 DS. Yeah, this is pretty much it. I mean, so we do have to do the integral. I have already done it a few times, so this is a little spoiler alert. I know that, so we're gonna end up with ZK omega 2 pi, and then once you substitute your bounds, we're going to get times 1 minus 1 over the square root of Z squared plus S squared. And that is our final answer. I feel like I haven't shown this in a bit, but this is the work. Yeah, pretty straightforward, a lot like the last one with the rings. Yeah, thank you.